Ever wondered how the chips that run your computers are made? It's a complex process that is carried out in an environment called a clean room. We are standing here today in one such clean room at the Center for Nanoscience and Engineering in the Indian Institute of Science. You see scientists working around me in clean room suits. They prevent our skin flakes from contaminating the room. This is a class 1000 clean room, meaning that the number of dust particles greater than 0.5 microns in size in 1 cubic meter is less than 1000. Outside the room, there are 35 million particles or more in the same volume. Yes, we breathe all that. The air that enters the room is put through filters to remove 34,999,000 particles to make it clean and exits through these holes in the floor. The chips that run your computers are made by robots. We will see how chips are made manually to understand the process. We start with a silicon wafer. This wafer is first put through a rigorous cleaning procedure and is the substrate on which devices will be made. A typical step in device processing is to deposit material on the wafer in thin film form. In this case, we are going to insert the wafer in a chemical vapor deposition reactor that allows deposition of materials using gas phase reactions. After a few hours, the wafer emerges and is coated with the material of interest. The foundation has been laid. It's now time to build our device on this wafer. It involves many steps with a mask defining every step. This is called a process flow. The entire mask set is designed and printed in advance. We will take you through the first two mask steps. The first step involves putting down metal pads at specific points on the wafer surface. A mask is first created on a chrome-plated glass plate. It is now time to transfer the pattern that is there on the mask plate onto the wafer surface. To do so, we will now travel from the chemical vapor deposition reactor to the lithography bay. Lithography means writing with light. You will see that the bay here is flooded in yellow light. It is ultraviolet, UV-free illumination. We will first spin coat a special chemical called a photoresist or PR on the wafer. It is special because it's chemically altered by UV light. After the PR has dried, the coated wafer and the mask are loaded onto a mask aligner and illuminated with UV light. Only those areas that are not masked off are exposed. After exposure comes development. The wafer is dipped in a chemical that dissolves our special chemical, the PR, only from those regions exposed to UV light through the mask. It's only these regions that the PR is chemically altered and hence made soluble in the developer. Voila! We now have a pattern transfer. In these regions from where the PR has been dissolved out and where the CVD material deposited surface is now seen, the metal pad pattern we desire in step 1 will be deposited. Now, you should be able to answer the question as to why the room is bathed in UV-filtered yellow light. The wafer with a patent photoresist now travels to the metal deposition bay, where it is loaded in a physical vapor deposition unit. Metal is vaporized and it coats the entire surface of the patterned wafer, both those covered with photoresist and the exposed wafer areas. The wafer is now subjected to a process called lift-off to get rid of the photoresist-coated metal. It is dipped in a solvent that dissolves the photoresist and in the process removes or lifts off the metal on top of it. The metal that is deposited on the wafer surface stays in form of the pattern that was desired. The first mask step we had embarked on, what appears to be a long time ago, is now over. Devices require that other patterns be transferred, but with a specific relation to the first one. To do so, the wafer with the first pattern is again coated with PR, and the entire process is repeated but with mask 2. Mask 2 is aligned using features on the surface of the wafer. This is the most critical step, as any misalignment here means that wrong electrical connections will get made. The device or circuit will then not work properly. The PR is exposed and the metal is deposited again. Post liftoff, the second pattern with a definite relationship to the first one is now realized. We have now gone through 2 steps. Similar processes are repeated to finish the device. This process has taken many masks, many different pieces of equipment, many material deposition steps, not just metals, and many hours of work. Time now to test the device we made. The devices that run our laptops and cell phones are extremely small, nanometers to micrometers in size. You can fit more than 1,000 of them in a cross-section of human hair. The features we just made are so minute that to contact them, to make electrical connections, we need very fine probes. The wafer with the completed devices is loaded onto a probe station, and the exact device to be tested from the thousands that we made on a single wafer is contacted. Voltages are applied, currents are measured. Looks like our transistor is working. The wafer we have just processed is divided into squares, along which we will now cut using a diamond blade to realize what are called dies. Each die has the devices or circuits we just realized using our 10 mask process. After dicing, the dies are now first mounted onto a package, and then wires are bonded to the very small features so that the external world can make electrical connections with the circuits we have made. The package is now closed. These are the components you see on any PCB inside an electronic device. The life of the wafer now ends, and that of the device begins.